Okay, so let us continue our discussion and let us have a recapitulation what we have discussed so far. So far, we have discussed one-dimensional steady-state heat transfer from extended surfaces. In order to analyze this, we have derived one governing differential equation. Then we have discussed its solution. Then for different cases, like for case 1, heat transfer from a fin of infinitely long length, we have derived temperature distribution equation and rate of heat transfer from that fin if attached to the base surface. Then for case 2, heat transfer from fin of finite length and insulated at the tip. And for case number 3, fin of heat transfer from fin of finite length and losing heat at the tip by convection. So for all these three cases, we could find out temperature distribution equation and rate of heat transfer from each type of these fins when they are attached to base surface. Okay. Now let us discuss the last case, case number 4. I'm not going to derive it actually. Rather, I'm giving the boundary conditions for this case and only the end equation. So the last case is heat transfer from a fin connected to two different heat sources, or you can say surfaces. This can also be given as heat transfer from fin with specified end temperature. Let me admit this student first. Okay, so what will be the schematic? There is a fin. Let's say this is one base surface at temperature Ts, and one fin is connected to this, and tip of the fin is once again connected to another surface at temperature TL. The fin is of length L. Here I can say Ts is greater than TL. Thermal conductivity of the fin is K. Its cross section is, let's say, circular. It is exposed to the fluid having temperature T infinity and convective heat transfer coefficient H. Okay. So how the temperature distribution equation can be given for this case? See here, the left hand face is connected to one source at temperature Ts, and tip right hand side or tip side is connected to another source at temperature TL. Ts is greater than TL, so heat transfer will take place in this direction. So how the temperature will vary, how the temperature of the fin will vary under such condition, I am interested to know. And how much heat transfer will be taking place from this fin from hot source, hot surface to the cold surface. I am interested in that equation as well. So let us first find boundary conditions for this case. The first boundary condition, as you can see here, Tx will be equal to Ts at x equal to 0, that is on the left hand side. In terms of excess temperature, I can write this as Tx minus T infinity is equal to Ts minus T infinity, or theta x is equal to theta s at x equal to 0. Okay. Now second boundary condition will be Tx will be equal to TL, because tip temperature will be equal to the surface temperature of the second source at x equal to L, or Tx minus T infinity will be TL minus T infinity. Or in terms of excess temperature, this will be theta x is equal to theta L at x equal to L. So once again, these two boundary conditions are there for case number 4. So these two boundary conditions are to be solved in conjunction with equation 7. That is the solution of the homogeneous linear differential equation of second order. So I will get temperature distribution and heat transfer rate equation. So I am directly writing, I have derived it. So let me write it for you. So temperature distribution for this case, that is Tx minus T infinity over Ts minus T infinity will be equal to TL minus T infinity over Ts minus T infinity sine of hyperbolic mx plus sine of hyperbolic m L minus x. Entire to the numerator is denominator. Sine of hyperbolic ml. This is the temperature distribution. Okay. Like we have derived for earlier cases. Okay. Similarly, on the similar tone, on the similar tune, I can find out heat transfer rate. That is, if the fin is connected to two different sources, one is at heat, one is at higher temperature with respect to other. So how heat transfer rate will take place through the fin. So we are interested in that equation. So again, I am writing this equation directly, and it is given in data book. Ts minus T infinity plus TL minus T infinity multiplied by cos of hyperbolic ml minus 1 over sine of hyperbolic ml multiplied by square root of HT K AC. So this is the rate of heat transfer. In all earlier cases, we have found out these two terms, equations for these two terms. So with this, I am able to cover all the 4 different cases. So I have started with derivation of this governing differential equation. This is the governing differential equation, equation number 6. For one-dimensional steady-state heat transfer from the fin. Then this is its solution, equation number 7, as you can see here. Then for case 1, for infinitely long fin, the derivation in some other page. Then for case 2, heat dissipation from fin of insulated tip. That is also in another, it is here. This is the equation of temperature distribution. Then this is the rate of heat transfer from fin with insulated tip. Then for case 3, heat dissipation from a fin of finite length, losing heat at the tip. So this is the equation for temperature distribution. This is quite lengthy. So this is the temperature distribution for case number 3. And similarly, rate of heat transfer from fin losing heat at the tip. And finally, for case number 4, when fin is connected to 2 different sources or its tip is at a specified temperature TL. So what will be the temperature distribution? This will be the temperature distribution, and this will be the rate of heat transfer from that fin. So this way I could analyze one-dimensional steady-state heat transfer from fin and under 4 different cases.